If we return to our convection cell, we find that the flow to the north in the upper atmosphere is deflected to the right by Coriolis. Conversely, the return flow to the south near the Earth's surface is also deflected to the right. This deflection limits the meridional, that is the north-south, transport of air. This results in a convection cell known as a Hadley cell that extends from the equator to 30 degrees north or south. Therefore, winds in the upper atmosphere move towards the east, and at the ocean's surface they move towards the west. These surface winds are known as the trade winds. Additional convection cells are formed at higher altitudes. At mid-altitudes, the Ferrel cell is responsible for the westerlies. These winds are directed towards the east. Near the poles, the polar cell creates the polar easterlies with winds directed to the west. These atmospheric circulation cells drive large-scale wind-driven ocean gyres. As shown in the animation of the global ocean, these gyres typically form surface circulation systems that are dominated by intense, narrow boundary currents on the west side of an ocean basin and broader, weaker return flows on the eastern side of an ocean basin. Transverse currents connect the north-south flowing boundary currents, thereby completing the circuit within the gyre. For example, the Gulf Stream is the dominant western boundary current in the North Atlantic, while the Kuroshio is the dominant western boundary current in the North Pacific. The Brazil Current and the Eastern Australia Current are the dominant western boundary currents in the South Atlantic and South Pacific. The Agulhas Current is the dominant western boundary current in the Indian Ocean. Another dominant current in the Southern Hemisphere is called the Antarctic Circumpolar Current. This current is unique in that it circles the globe. The surface currents on either side of the equator are dominated by the westward flowing north and south equatorial currents. They are separated by an equatorial countercurrent, which flows to the east. The question arises as to how the gyres form. Here, a simple process known as Ekman transport helps us to understand why the surface ocean circulation is dominated by gyres. As we've discussed, Coriolis deflects a current to the right in the northern hemisphere and to the left in the southern hemisphere. Here, for the moment, we consider the northern hemisphere. The wind initially blows surface water in the direction of the wind. However, due to Coriolis, the net effect is that the surface current is deflected to the right. This is referred to as Ekman transport. If we zoom in on the North Atlantic gyre and consider first the trade winds, these winds blow towards the west on the southern boundary of the domain under consideration. Due to Ekman transport, the water is deflected towards the right. Similarly, if we consider the westerlies blowing towards the east on the northern boundary of the domain, again due to Ekman transport, the resulting surface currents are deflected to the right. We can see in the animation that the net effect is to transport the water into the center of the gyre, creating a region of higher sea surface elevation in the center of the ocean basin. We refer to this as a high in the animation. Associated with this sea surface pressure gradient is a geostrophic current. As we found for the case of the weather map, the current is along the isobars. This results in a strong surface current in the direction of the wind. While we may have anticipated this result, it's the geostrophic effect which is causing this. Due to the variation of Coriolis with altitude, strong western boundary currents are formed through a process known as westward intensification. Associated with this, the high-pressure center is shifted westwards. In the North Atlantic gyre, the resulting current is known as the Gulf Stream. Similar gyres also form in other ocean basins, as we've discussed above. If we look at the subpolar gyre, which is located to the north of the North Atlantic gyre, we find that the southern boundary of the gyre is forced by the westerlies, and the northern boundary at about 60 degrees north is forced by the polar easterlies. In this case, Ekman transport results in a low-pressure system at the center of the gyre. The resulting geostrophic flow is counterclockwise around the low. However, due to the variation of Coriolis with altitude, we again find westward intensification. Hence, the subpolar gyre in the Atlantic and the circulation in the Gulf of Alaska and the Pacific both form strong western boundary currents, but the sense of surface circulation is opposite to that of the mid-latitude gyres. These systems are responsible for the circulation of the upper ocean to depths of up to 1,000 meters and play a major role in moderating the Earth's climate. For example, the Gulf Stream plays an important role in transferring heat northwards, such that northern Europe experiences milder winters. However, Ekman transport due to the wind only provides part of the explanation for the oceanic circulation.